Hello, everybody. I'll today introduce our whole NVIDIA Gen AI stack to you. Feel free to interrupt me, and if you have any questions or if you want me to skip a few sections and slides, maybe because you've already been introduced to that, let me know and we can keep this very interactive. And without further ado, let me just flip to the sides. So yeah, we all know with Generative in 2022 when ChatGPT came in, we saw a true explosion in all the AI capabilities, and a lot of companies in 2023 and enterprises started experimenting with the technology and the software. We started looking at developing applications that would probably soon redefine the markets. A lot of trials, tests, proof of concepts when generative models like Llama 2 and platforms are being powered by very AI foundry like the NVIDIA is developing. And we all these are not just experiments, all of them were trying to build blocks for this new digital infrastructure that we are seeing. Now in 2024 and 2025, all the experimentation has paid off, and we are seeing applications being pushed into core production. And we're not just looking at production use cases, but we're also seeing an ecosystem where generative AI is the engine driving a lot of innovation, efficiency, and a lot of growth. And this is also going to be our focus for our GTC conference this March, where a lot of announcements are going to be made along with our partners and customers. And we'll speak to you about all the production ready solutions that we've been enabling. You'll see that today generative AI is capable of learning and understanding everything, right? You can move from different modalities and ingest a lot of modalities and convert it to different modalities. You can predict the images from text. You can drive PDFs to extract videos from PDFs or convert that to videos, create a podcast from PDFs. And we're seeing a lot of this back and forth going from different foundation models and different modalities. But that also poses a lot of challenges. As we are building these AI applications, what we are noticing is on one side, we have these managed generative AI services. They're very easy to use. They have simple and user friendly APIs, which allow rapid development and quick launch into the AI sphere. And they also give you a fastest path to getting started with AI. Requires very little infrastructure setup, and that enables you to go quicker and you have a quicker go-to-market strategy. However, these benefits come with a certain trade-offs. The infrastructure is typically limited to a managed environment and data, including the prompts that you can share externally. There's also a dependency on the service provider system and protocols. You can have limited control with your generative AI strategy, and that can have a significant drawback for some organizations, especially when you have stringent data governance and privacy standards. On the other flip side, we are seeing a lot of open source development. The main advantage to this is that you have a lot of flexibility when you can run your AI models anywhere across different data centers and cloud environments. You can easily manage your data within a self hosted environment, and that's vital for compliance or any proprietary concerns. However, there's this increased control, right? It requires a greater commitment to the infrastructure. You need to tune different parts, write custom code for APIs, and sometimes even more intricate model fine tuning to optimize your performance. And you also have to be responsible for ongoing maintenance and updates, and that can lead to significant resource commitment. Has your organizations already picked one of these approaches? And if so, what challenges are you facing? We would love to know more about that. And to make this journey much more easier, NVIDIA provides NIMs right now, or these are also called NVIDIA NeMo Inference Microservices. They provide best of the both worlds, and it's a simple way to deploy AI models using a standard API path. What we've done is we've adopted industry standard APIs in conjunction with NVIDIA cloud standards. Um, to facilitate this integration and interoperability across systems. Now, for those working in specialized fields, we also provide domain specific code for a variety of NIM domain categories, including large language models, vision language models, video processing, healthcare, and a lot more. So, this ensures that you have all the tools necessary for your specific use cases. They are you'll see it's very the NIM comes in a form of a container, which is very portable. You can deploy it anywhere and you can have the control of your own AI applications and data. It's very easy to use. The containers are pre-built and we are continuously maintaining these microservices. You have enterprise support with API stability, security patching, and quality assurance. And moreover, our reference engines are optimized for each model and hardware SKU. And that delivers unparalleled performance no matter what your application is, right? We also recognize the importance of the customization that's needed. So we offer support for custom models built by users for any target use cases, ensuring that you can adapt this technology to your own unique requirements. And all of these NIM containers are built on the NVIDIA AI Enterprise base container, and that guarantees a reliable and secure foundation for all your AI applications. And I'll explain the NVIDIA AI Enterprise in a couple of slides. So if you want to develop, if you want to have the fastest path to develop AI models on accelerated infrastructure, NIMs offer that flexibility to do so while maintaining control of your own AI applications and data. You don't any longer need data scientists and ML AI engineers to spend a lot of time on integration, optimizing inference, and so on. We offer day zero support for all the generative AI models, and we provide a wide range of choices across the ecosystem, right? Whenever we are in touch with all the latest Llama models, Mistral models, and so on. And cost efficiency is key here. So we've worked hard to improve the total cost of ownership, giving you the best latency and throughput. And you can also run it on any accelerated infrastructure. We work with all the major cloud providers and other partners to help you achieve this. So you're not losing any accuracy, but at the same time, the models are as effective and precise as possible. With that, I have a single slide here showing you what is the difference between NVIDIA and NIMS. And you can also do this your own self, but it also takes a lot of engineering resources to deploy optimized and accelerated models. With NVIDIA and NIMS, you can just deploy them in 5 minutes, but if you want to do it yourself, it can take upwards of a week. And that's because you need to implement the API layers for each domain, for each model family, according to the standard specifications. You have to build these engines manually and customize them for workload and hardware specific requirements. And there's a lot of custom logic, manual setup and configuration. But we've automated this whole process for you. And further, there is extensive workload specific QA and support matrix validation. We deliver this with NVIDIA AI Enterprise. To explain this a little more, let me also double down on AI software security and stability. Right? If you take a closer look on what it takes to manage a secure and stable AI stack, you'll see that the stack is built from many different components, and many of them are from open source projects. As you can see on the graph on the left side here, it's a visualization of only one component AI of the AI software stack, which is the NVIDIA's Triton Inference Server. Now, this stack is made up of 562 packages, and most of them are third party open source packages. So, all the green lines between these packages are basically dependencies. With so many packages, there comes a high likelihood of vulnerable code increases. And because of the many dependencies, the complexity of fixing these vulnerabilities also increases. So, managing all the CVEs in the stack with all these dependencies is very resource intensive. It requires constant monitoring and scanning. It requires significant expertise to understand the impact of a dedicated common vulnerability and exposure to a certain application. It also requires engineering expertise to be able to perform that patching and security updates without any dependencies. And it's not enough to do all of this at once. You need to do constantly monitor and update them, and it's a continuous process. So we recognize that this is a huge task and a task many enterprises are not prepared to take it by themselves. So with NVIDIA AI Enterprise, we do this work for you. And you'll see that with NIMS, we promise improved efficiency out of the box. Here I'm showing you an example or a benchmark from the Llama 3 8B instruct model when deployed on a single H100, assuming a use case has input 1,000 tokens and an output of 1,000 tokens, and we are having a concurrent requests for about 250. With NIM out, when the NIM is turned off, you'll see a NIM throughput of about 3,500 tokens per second. And maybe the time to first token is about 1.7 seconds. But when you turn the NIM on, our throughput improves at least 2.6 times. Now you have about 9,000 tokens per second, and the time to first token is reduced to about 3.4 milliseconds. So that's the big difference that we are seeing right out of the box. And not just that, NIM also accelerates the entire AI factory. The performance gains that you're seeing not only improve the overall efficiency of the data center, but the NIMs enable you to accelerate the AI factory itself, so that you're maximizing token generation and you're minimizing the total cost of ownership. And this is what roughly an AI factory could look like, right? Including the cost of your data center in terms of compute, network, power storage, etc. And now with just the hardware, you have decent throughput out of off the shelf with Llama 3 LLM, and additional tuning and effort could be spent to improve this number. But again, that requires a lot of engineering expertise. So with NVIDIA AI Enterprise, you'll see that just a 7% additional cost for a software, it brings a significant benefit where the throughput jumps to about 500,000 tokens per second. And that's a 5x improvement. And these benefits don't stop here. We also support SNA, regular security patching, lifecycle management, and so on. And the estimates are here, right? If you have a 100 million data center estimated based on TCO, and these costs proportion from a typical Hopper AI data center, and that means roughly about 1,600 H100s. And if you add the NVIDIA AI enterprise on top of it, it's about $107 million that go into building a data center. But if you're comparing the token throughput, maybe from about 5.6 million tokens per second, we're again extrapolating that 2.6 throughput, that's almost about 14.6 million tokens per second. Hence, accelerating all of your applications within your AI factory. Now, what is NVIDIA AI Enterprise? NVIDIA Enterprise is a cloud native software platform for developing and deploying these production grade AI solutions. It includes all the optimized NIM inference microservices that enhance model performance and speed up the time to deployment. It also includes all the software developed kits and frameworks that support these AI applications across many domains. It includes tools and libraries that accelerate data analytics, model training, customization, any optimization and deployment. It's basic. It also includes infrastructure software that helps manage AI clusters at scale. And this could be across the edge and data center, both bare metal and virtualized. And the software supports on-prem, edge, and cloud so that it provides maximum flexibility as you need it. Now, NIMs are the fastest way for you to, they're very, sorry, let's go back one slide. Like I said, it's the fastest way to deploy AI models on accelerated infrastructure. So you can choose your platform and where you want to deploy, whether it's Microsoft, Azure, cloud, data centers, or even PC. We have the NVIDIA API catalog, which you can go check out. We bring in models from every model from maker and provider like Meta, Mistral, Google, and to all the open source models that we are seeing, even from universities like MIT. You can check out all of them on build.nvidia.com. In fact, the build.nvidia.com enables you to interact with state-of-the-art AI models through our API catalog. We have many NIMs available for different domains, like I said, LLM, speech, digital biology, multimodal or visual generative AI. You can generate an API key from our catalog, and developers can tap into all these pre-built models, deploy on Kubernetes with ease, test them out, and once you're ready, you can pick a NIM that you want with the NVIDIA AI Enterprise software and download and just deploy them and go into production. And not just a few of these domains, right? We have an NVIDIA NIM, in fact, for every domain, starting from text, visual models, RAG, speech, healthcare, computer vision, simulation, and there are so many models, and these are growing every day. We also have our own models paving the way for generative AI, and some of them top the leaderboard. Right? For example, we have the best commercial chat models, reward models, a few RAG models, document and content retriever models, best routing optimizations like with the co-op library, and even automatic speech recognition models. So you can feel free to test them out. I'll take a pause to see if any of you have any questions about NIMS. If not, I'll move on to the next, which is Nemo Retriever.
I have a question. In one of your previous, video. In one of your previous slides, you said NIM on and NIM off. I wasn't completely sure what that meant.
Yes, so NIM is basically an inference micro container. What it does is if you pick for each NLM or any large foundation model, we have a pre-built container. Now, this container accelerates, it's optimized for inference such that you get maximum throughput and lowest latency out of the box. So when you deploy this model through the container, that's what I call as NIM on. And when you don't have the container, but you're simply deploying it through the weights, it's NIM off.
Got it. Thanks.
Yeah.
If you need help unmuting, use the raise hand feature and we will help you. I think I'm muted.
Awesome. I'll move forward about Nemo Retriever. So Nemo Retriever again is a collection of microservices that's built with NVIDIA NIM. That can be combined with any third party or even just NVIDIA microservices to build generative AI pipelines for RAG or retrieval augmented generation. Now, these RAG pipelines today can be used to build agentic workflows and that can address many different use cases. For example, you want to build AI agents for analyzing security vulnerabilities and software security, or you want to build personalized shopping advisors for retail customers, or just AI chatbots that provide multi-turn human-like responses. You have AI agents for generating recommendations for supply chain planning, any virtual assistants for customer service, or even a digital human-based AI virtual assistant, right? So all of these applications underhood are driven by something called RAG or retrieval augmented generation. Now, before we dive into what we offer in the space of retrieval augmentation, I would just want to talk to you about how you build these agentic workflows, right? Now, in the core, data is fundamental to the evolution of all of the generative AI and even the next wave of agentic AI that we will see. There will be about, just in 2024, there are reports on how 11 zettabytes of unique enterprise data is being created, and it's projected to grow to about 20 zettabytes by 2027. Now, out of this, 83% of it is unstructured, and half of that data is audio and video. So, every enterprise will need an AI query engine that can use something like RAG to connect the workforce to enterprise knowledge base. Now, AI agents then can perceive, reason, and act and turn this knowledge into action. So, to give AI agents this access to this large amount of diverse data, you need an AI query engine that efficiently processes, stores, and retrieves data to augment the generative AI model inputs. And today, the most common way of doing this is to RAG, and you can, by ingesting all that available data, you can go beyond simply analyzing the metadata, which not only provides surface level information, such as who created this file or when the file was made, but it also has the ability to understand the actual content and the data itself. And to do that, an AI query engine must be able to access knowledge across structured, semi structured, unstructured, and even metadata sources. And this includes a lot of data types and multimodalities like PDF, images, video, and so on. You want a capability of efficiently being able to process this data at petabyte scale so that all that knowledge is available to every generative AI powered application and agents in a very short period of time. And moreover, you want to provide high accuracy and performant retrieval and re-ranking of this knowledge and information from multiple sources to augment the inputs that we provide to generative AI models. So AI query engine must be able to do all of this simultaneously. Now that we've talked about data engine, but also let's talk about the data factory, and that's the data flywheel. So an AI query engine must be able to store and leverage these learnings from an AI powered application and agents that are in production and automatically increase the knowledge of the enterprise. And that enables you to create an AI data flywheel. So think of it like data is the new raw material tokens is the new commodity, and NVIDIA is software is the token generator for the AI factory. And that way, every single company will be able to produce digital intelligence. Now, to be able to build this data flywheel, and at the core of it is the RAG application, Nemo retrieval models and Nemo retrieval offer microservices empowers you to build these RAG applications. Now, what comes at the Nemo retriever is a collection of text embedding and retrieving and re-ranking NIMs, which I'll cover in a little more detail in a moment. But it also has a Nemo retriever microservice that orchestrates the overall retrieval workflow that NVIDIA provides in the form of a reference architecture. So here I'm showing you how a typical architecture could look like, where you have an ingestion pipeline and you have a retrieval pipeline. And we provide a lot of building blocks, both for ingestion and for retrieval. We also provide use case specific AI workflows that you can leverage as starting points to build these RAG applications. So some of these use cases are like AI agents, generative AI copilots, generative AI virtual assistants, and even just basic summarization, right? So these are all retrieval models have optimized inference engines. They're state of the art. They can be customized further. You can fine tune them for improvement in accuracy. They are flexible, and you can pick the pieces that you want to deploy. It also comes with accelerated vector search, and it's production ready. When I say we accelerate vector search, and underneath we have NVIDIA CoVS, which is an open source library for GPU accelerated vector search and data clustering that just again enables higher throughput and lower latency, and in fact faster index build times. By integrating CoVS into vector search, we are seeing developers can improve the efficiency of semantic search within their pipelines and on their applications, which include information retrieval and retrieval augmented generation. Underneath, you'll see that CoVS exploits the parallel architecture of NVIDIA GPUs. So we are parallelizing the whole retrieval and embedding process. And we also leverage some complex algorithms like IVF-PQ, IVF-SLAT, CAGRA, and all of them. So GPU acceleration of vector similarity search, in fact, we have open benchmarks that we can share with you for large scale, high performance solutions. We also work with a variety of embedding vector stores like Phase, Milvus, Redis, VV8, DataStax, and Lucene. All of them, we are working with them to improve the vector search. Here is some of the benchmarks that I can share with you. Consistently for many months, we've been topping the MTEB leaderboard, which is the embedding leaderboard. Our models are one of the best in retrieval, overall retrieval capabilities, and even re-ranking capabilities. If you look at the vector search, we've improved our vector search or index building time by 5 times and throughput by 8 times. So that directly impacts the latency of your overall application. We have multiple retrieval NIMs, starting from a purely English text embedding model, which is the NV Embed QA5, to multilingual models. We also have optimized community embedding models like the Snowflake Arctic Embed model. We also have multilingual re-ranking models. And recently, we've also opened up world-class multilingual and cross-lingual text embedding and re-ranking models based on Llama 3.2. And all of these are available again on build.nvidia.com, where you can play with it and plug it into your applications and see the accuracy that these models can provide. Again, to just share with you some benchmarks, with the NV Embed QM Mistral 7B V2, you'll see we again are looking at twice the throughput for faster retrieval, again with NIM off and on. This also leads to 30% fewer incorrect answers because we've improved the accuracy by developing internal data sets itself and fine-tuning these with various approaches and strategies. Not just that, right? Why do we need a re-ranker on top of embedding model? What are the differences here? So re-ranking models often take in text chunks from the documents and the question, and they create a combined representation of both and then score the relevance of two texts. Whereas an embedding model is, along with the heuristic metric, fundamentally are doing the same thing. But how do you know which one is better to use? So that answer lies in the question itself, and you need to understand the trade-offs that are being made. So embedding models are considerably faster and cheaper than a re-ranking bot, but a re-ranking model is significantly more accurate. So to make the best of both models. You can use a lighter and a cheaper embedding model that can be used to identify a small pool of relevant chunks to a user's question, say about 100. Then a heavier and a more accurate re-ranking model is used to identify the most relevant chunks. So if you have multiple retriever pipelines that are being used to extract the top 5 most relevant information from each source, the re-ranking model can then be used to narrow down the best piece of information that you have. So over time, you'll see that how we've improved accuracy, right? You start off with traditional retrieval models, and then we brought in the NV embed QA. Then we fine tuned the Mistral 7B model. And then we added a re-ranker on top of it. And this step by step increments has led to 30% fewer incorrect answers overall. Not just that, it also improves your data storage efficiency, right? If you look at the storage volume versus how you can reduce your embedding dimensions, raw text itself, if you start with about 1,000 GB, a baseline vector embeddings without any optimizations can create about 2,500 GB of storage volume. But we've reduced these embedding dimensions with our retriever, made it more efficient. And when the NIM is on, we've reduced that whole volume to at least just 70 GB. So you're also improving the data storage efficiency there. Like I said, we also have state-of-the-art multilingual and cross-lingual models for most accurate responses. We've open sourced Llama 3.2 embed models and re-ranker models. Again, this provides about 1.8 and 1.6 times improved throughput. And we're seeing about 30% fewer incorrect answers on most benchmarks that I've shared with you down here. So just to give you an overview of what we have in the NEMO retriever space. We also have other NEMO microservices. To be able to build, customize, and deploy generative AI models, we have the whole suite of NVIDIA NEMO microservices, starting from data preparation to training and customization, and finally going into deployments. Some of the things that we've made sure with these microservices are: one, you can easily customize these models with industry standard APIs. We want you to build these custom models faster and lower your development costs, along with scaling of data curation, training, and easy model evaluation. To enable you to achieve higher model accuracy, we now have these as microservices. So every module like data curation, model evaluation, and guardrails is now a microservice. And all of them come together to support end-to-end model customization workflow. And you can customize anywhere for security, privacy, and flexibility reasons. And we have enterprise grade software supported with NVIDIA AI Enterprise. I'll touch on each of these. I'll give you a high level overview of each of these modules. But what I'm trying to say is, if you want to build your enterprise AI flywheel and you want to create more customized and deploy these workflows, you will need the other modules as well, starting with data processing, model customization, evaluation, guardrails. And then once you have the customized model, how do you deploy an optimized customized model? Now, to do all of these, we have these 5 microservices, which is the curator, customizer, evaluator, guardrails, and finally the NIMs that I mentioned before. Just to give you a small overview of a flavor of these microservices, right? Starting with NEMO Curator. Now, some of the biggest challenges that we are seeing is when you're curating data to either create foundational LLMs or fine-tuned LLMs or even sovereign AI. The typical challenges are you can deal with a lot of poor data quality, a lot of duplicate documents, personal information, text formatting issues, toxic or harmful content. So all of these pose challenges to the data processing. Longer processing time itself, data often is at internet scale, trillions of tokens, and it requires significant compute and time to process. And further, this data that's being processed is not scalable. As it is increasing at a high rate, your processing pipelines also need to scale according to those needs. Then third, the other challenge is multiple modalities. You need to create specialized pipelines to manage and process data of different modality types. Image is processed differently versus text. Video is processed differently versus images, and so on. Now, most of the existing libraries rely on CPUs, and that can lead to longer processing times. And developers often build their own fragmented solution for different steps in data processing pipelines. So often they are very fragmented and are not repeatable. And these solutions also provide iterative jobs instead of scaling efficiency. So to bridge these gaps, we have NEMO Curator, which provides high accuracy with less data, less training compute, faster processing. Underneath, we are leveraging the NVIDIA GPU accelerated rapids library, which can enable you to do very accelerated deduplication, quality classification of your data, and so on. You can scale up to 100 plus terabytes of data across multiple nodes, very easy to deploy. We have a lot of classifier models that can help you to do quality classification on your data, and further, you can deploy it anywhere, just like other NEMO microservices. Here again is that I'm sharing with you a couple of benchmarks that we are seeing on NEMO Curator. So if you have to process the Red Pajama V2 data set, it has about 80 TB of data, which is about 1.78 trillion tokens. With NEMO Curator, we can process this whole data 16 times faster and reduce the processing time to about 0.65 hours. You're also reducing your total cost of ownership by 40%. Um, and we are also observing linear scaling, right? As you add the number of nodes, if you add 4 H100 nodes, your processing time just takes about zero point 0.5 hours, whereas with a single node, with a single H100 node, you'll see about 2 hours. So that's the kind of linear scaling that you observe with NEMO Curator. Then we have NEMO Customizer, which is again a model customization microservice, which you can integrate within your AI platforms. It gives you state-of-art customization techniques like LoRa, P-tuning, SFT, DPO, and just one API call to model customization, right? Again, we are hugely bringing in advantages with improving the throughput time and reducing the training time. And again, you'll observe the same kind of scaling with NEMO Customizer. And lastly, the NEMO Evaluator. As you're developing your customized pipelines, you would want to evaluate any part of your LLM powered application, and this will get just increasingly complex with agentic workflows. So with the NEMO Evaluator, you can launch evaluations with standard APIs. We have a lot of community benchmarks, pre-built similarity metrics, also state-of-the-art LLM as judge techniques, right? You can deploy them anywhere, any part of your application, and bring it and build it within your AI enterprise data flywheel itself. And then you have NEMO guardrails. Again, this is complementary approach to RAG to reduce your hallucinations. You can build rails and target it for your specific use case and enterprise policies. It'll help you provide content moderation, reduce hallucinations, avoid any toxicity, off-topic dialogues, make sure personal information is not shared, and also detect any security jailbreaks. You can apply guardrails during data curation, input to the generative AI model, and even while generating the response. So it's very flexible. You can orchestrate these rails to improve your protection rate while reducing latency, because we've optimized guardrails itself so that you can increase throughput and lowering costs, so that when you're applying each guardrails, it's not adding additional latency to your application. Again, easy integration with third-party APIs like OpenAI, ActiveFence, TrueEra. You can choose any of your APIs. And there is also fundamental capability of native integration with any popular GenAI tools like LangChain and Llama Index. So it's very flexible. And overall, all these microservices simplify and ensure consistency of repeatable workflows across teams. If you just choose any of the open source libraries and start building your pipeline, it can have at least 22 steps that you need to optimize and fine tune. But with Animo microservices, you just have to deploy 5 API calls, put this whole workflow together. So that's a little about all the NEMO and NIMs and microservices. I would also lastly like to touch upon a little on the agentic AI and NVIDIA blueprints and what we are working on in this space. Fundamentally, how do these AI agents work? They act very independently to achieve specified objectives. They are AI agents, they are often adapting to new information dynamically. You add a lot of components and modules like a planning agent, you're adding memory to the workflow, you're improving reasoning, you're connecting these LLMs to multiple agents or tools to accomplish some objectives. For example, you want to create a virtual agent that's capable of managing schedules, automatically can make purchases, or you're solving problems. Now, each agent always comes with a data flywheel that I described previously. Now, the whole application itself, building process starts with a NIM. But in order to build the data flywheel, NVIDIA NEMO could be used to create that data flywheel aspect that I spoke about. And and in fact, Nemo will help you accelerate this whole intensive stages of AI agentic development lifecycle. And we have a very broad ecosystem of partners who build on Nemo and NIM to make it easy to develop your own AI agentic applications, right? So agents like we see, they'll open up computer programming to every employee of the AI enterprise. So instead of manually programming, for example, a coding application, instead of manually programming every line of code and compiling applications for your CPUs, you can simply prompt the LLMs to write the application for you. And AI agents will then plan what tools you have to use, what is the best answer to the question, retrieve that information across tools, and even talk to other agents before critiquing the results and deciding whether you want to keep that or not. So that's, but you have to build this workflow, and they relatively use large language models to generate, plan, and reason out the whole problem. And most often, I think some of the issues that we are seeing is latency issues with agentic workflows. And some of the key agentic AI tasks here are that we are seeing across all applications are being able to solve graduate level complex questions, being able to solve graduate school math. Can we enable function calling? How do we add document retrieval to agentic workflows like just RAG? Or even how do we use these agents for coding tasks or other multitasks, right? Like the MMLU benchmarks that we are seeing. Or can we get these agents to follow instructions? So all of these tasks are some of the things that we want typical agents to be capable of. So in this space, we just announced our Llama Nemotron models. Now, but why do we need these models? Because agentic AI, they require advanced models to handle a variety of tasks with precision, adaptability, and efficiency. So if enterprises may need this kind of high accuracy for a wide range of agentic tasks so that they can handle complex real world scenarios effectively, you want these models to be commercially viable for seamless integration into your environments and offering full control and the ability to run various applications. And also, businesses have unique requirements. Sometimes you want to allow for fine tuning these models for specific tasks so that you have specific tailored outcomes. And then running multiple AI agents can be resource incentives. So you want your models to be optimized for compute efficiency. So we introduced different kinds of Llama Nemotron models that are tailored for building AI agents. You have Llama Nematron Nano, which is very low latency model, and it's also useful if you want to do it deployed for edge agentic applications. Then we have Llama Nematron Super model, which gives you much more accuracy with with a lot of with a very good throughput on just a single GPU. And then lastly, we have the Ultra Llama Nematron model, which gives you the highest accuracy, but for data center scale applications. So on a diverse agentic tasks that I spoke previously, these models give you leading accuracy, state of the art judge and RAG models. You can accelerate your time to market, simplify your development with our NIMs, blueprints, and that's how these models would be served. Further, they are open source, and we also have enterprise grade for these models here. I also want to talk to you a little about the NVIDIA Cosmos Nematron. These models are vision language models that were again recently introduced into the space to enable image and video understanding along with the LLMs. Again, we have these nano, super, and ultra for multimodal intelligence extraction. So again, if you're building any of these agentic tasks that leverage video data and you want to develop something like video search and summarization, these models could be leveraged for that, for those use cases. And then I also want to talk to you about the Nemotron 340B family models. This is for synthetic data generation pipeline. Often, a lot of data is needed to fine tune and train these models from scratch. And manual labeling is time consuming, costly, and also has human bias. So synthetic data generation can address this training data bottleneck. In fact, we are seeing that 60% of all the leaders are saying that synthetic data can be adopted to overcome the lack of data accessibility and annotation that's related complexities. So to address that challenge, we have these synthetic data generation pipelines with the Nemo Curator, and we have these Nemotron 340B family models. For example, the instruct model itself is fine-tuned to generate very accurate synthetic data for a variety of use cases. Once you have the generated data, you could use the reward model to generate response scores so that you can then go back and train and fine-tune your models. And lastly, we also have the Nemo Aligner library, which comes with a lot of algorithms like the reinforcement learning, TPO, SteerLM, pins, all of these algorithms help you align your foundation models with the synthetic data that you have created to a specific task that you or a use case that you want to support. Again, Nemo Aligner is available on GitHub and it's open source. So you can go ahead and check out all the examples that we have published in this space. And lastly, like I said, we have all the building blocks that we need to create these agentic workflows. We're seeing how agents, specialized AI agents, will be connected to various applications like Teams and allowing them to work together to find solutions to your most complex business challenges. So, most often, for your own enterprise, you might need one supply chain agent, a healthcare agent, a service agent, a research agent, a data engineer agent, and so on. And you will need a framework. You'll need to build a framework where these agents can interact with each other and also power your end use cases and applications. So to, to help you start with this journey, we have NVIDIA agentic blueprints and reference AI workflows. Now, these workflows are pre-trained for specific use cases. They can be customized further. They include reference code for constructing the workflow using our NVIDIA AI Enterprise software, NIM microservices, NVIDIA NEMO, along with all the tools and documentations that is needed for deploying this in your own environment and customizing it to your own data. All of the blueprints include a reference architecture, which documents API definitions and how the microservices interoperate and a lot more. So the collection of NIM blueprints include AI virtual assistants, digital humans, multimodal PDF data retrieval, high throughput version screening, and many more will follow. So we are building these blocks for even for the AI query engine. You'll see for every AI agentic workflow, there'll be a whole reference pipeline in the form of a blueprint that you can take it, customize it, and fit it into your application. So that's what the blueprints bring to you. I would just want to speak a little bit on the multimodal PDF data extraction blueprint that we have. Now, how is this helpful? We have trillions of PDF files. Every enterprise has this, and they're generated every year. Each file has multiple pages, various types of content, including text, charts, images, and tables. And we want to, this is a gold mine of data that you want to extract and use it for your applications. You want to build GenAI pipelines, you want to build RAG pipelines, again, to improve productivity and to power a lot of users. So the multimodal PDF data extraction blueprint enables organizations to extract the knowledge contained in massive volumes of PDFs. It can enable you to talk to your data and also connect maybe to an expert or a digital human, enabling your employees to make smarter decisions. So through this, if you look at this workflow, PDFs are parsed to separate modalities like text, images, charts, tables, plots, and other diagrams. And you have new microservices that are being leveraged to accurately extract textual data from charts and tables. That extracted information is then filtered to avoid any duplicate chunks. And then we leverage the Nemo retriever embedding them to convert that chunks into embeddings and store them in a vector store. So when a user submits a query or relevant information is then retrieved. So we have both the ingestion pipeline and the retrieval pipeline. You can, when the query comes in, the relevant information is retrieved from the vector store of all the data that we've just ingested. And then the Nemo retriever embedding NIM embeds that user query to retrieve the most relevant chunks using vector similarity from the vector store. And then The re-ranking NIM on top of that re-ranks the results to ensure the most accurate and useful chunks are responded to the query. And then with the most pertinent information at hand, you'll have finally the LLM NIM that generates a response that is informed, accurate, and contextually relevant. So we've put together this whole workflow for you, which you can go download and just deploy it. And I can also share a few benchmarks with you here. You'll see that with the multi-model PDF ingestion throughput, we've brought in all our NEMO microservices and NIMs together and in just one container. And you'll see that this optimization, we've improved the throughput of the whole pipeline with 3 times. And we are also seeing our early internal testing is very promising. It's showing up to 20% fewer incorrect answers. And it also enables multimodal document ingestion, right? So it includes that. So this is something that you can also go try out. We have various other blueprints, but I just want to show you an example of what one blueprint does. So that is all I have for now. I've covered various topics. I would love to know what are your interests if there is something that you want to learn more about.